In 1895, a young 16-year-old named Albert Einstein envisioned a scenario, chasing a beam of light. This seemingly simple imaginative exercise would eventually transform the world's understanding of the universe. But how could one thought hold such immense transformative power? To understand Einstein's groundbreaking theories, it's crucial to first delve into the foundational work laid by Sir Isaac Newton, the renowned classical physicist. Newton's seminal work, Mathematical Principles of Natural Philosophy, published in 1687, introduced his three laws of motion and the law of gravity. Observing an apple fall prompted Newton to ponder a critical question. If the apple falls, does the moon also fall? This query led him to unveil the law of gravity, stating that every object in the universe exerts a force of attraction on another object. This force is responsible for phenomena such as Earth's gravity, the moon's orbit around Earth, and even the existence of the universe. However, Newton's revelations left significant questions unanswered. Mysteries persisted. Why do objects attract each other? What precisely is the source of gravity? And what causes irregularities in Mercury's orbit? The answers to these mysteries emerged during the era of Albert Einstein. In 1915, Einstein introduced his theory of general relativity, often termed his theory of gravity. Through this groundbreaking theory, Einstein elucidated the nature of gravity and its origins, resolving the unresolved queries left by Newton. Notably, Einstein's theory provided explanations for phenomena like Mercury's precession, which had baffled scientists until then. In 1905, Albert Einstein introduced his theory of special relativity, a pivotal moment in scientific history. This theory fundamentally addressed the behavior of objects in motion, particularly concerning the speed of light. However, it had limitations. It didn't apply in scenarios involving gravity or accelerating objects, leaving Einstein with unresolved questions. It wasn't until 1907, during a moment observing a window washer on a ladder, that Einstein experienced a breakthrough. Contemplating what he would sense while falling, he envisioned himself in free fall, realizing that during descent, the ground wouldn't push against him. This realization began to piece together aspects of his understanding, but it wasn't yet complete. Continuing his thought experiments on falling, Einstein imagined himself in a room devoid of windows. If the room were situated in a spacecraft accelerating upwards at the same rate as gravity, 9.8 m/s², on Earth's surface, the observer inside would experience the same weight as on Earth. This revelation struck Einstein profoundly. He realized that the observer wouldn't discern whether they were in a spaceship or on Earth solely based on their weight. This understanding marked a critical turning point in Einstein's quest for a comprehensive theory that would later lead to his theory of general relativity, ultimately reshaping the scientific understanding of gravity and the fabric of space-time. Indeed, Einstein's realization of the equivalence principle was a pivotal breakthrough in his pursuit of understanding gravity and its relationship with acceleration. The equivalence principle posits that an object experiencing acceleration without gravitational influence is indistinguishable, in terms of its behavior, from an object affected by gravity but at rest. With his theory of special relativity, Einstein had established a framework to comprehend scenarios involving non-accelerating objects and the speed of light. However, his aim to reconcile this theory with gravity persisted, leading him to conduct further thought experiments. One of these experiments involved imagining a laser beam directed across a room in a spaceship accelerating upwards at the same rate as Earth's gravity. In this scenario, Einstein realized that due to the equivalence principle, the laser beam's path would appear slightly curved or lower on the other side of the room. This observation hinted at the idea that gravity might influence the path of light, thus offering clues towards integrating gravity into his theories of relativity. This critical thought experiment laid the groundwork for Einstein's subsequent work on his theory of general relativity, which provided a unified framework encompassing gravity's interaction with space-time, shaping the modern understanding of the cosmos. Einstein's imagination and deep thinking led him to a profound understanding of gravity and its effects on light, fundamentally altering our comprehension of the cosmos. His thought experiments around the bending of light unraveled the idea that gravity warps space itself, laying the foundation for his theory of general relativity. Initially, Einstein's contemplation of the light beam's behavior within an accelerating spaceship suggested that gravity might be influencing its path. However, this notion seemed contradictory to the principle of equivalence, which posited that gravity and acceleration were indistinguishable. To reconcile this, Einstein speculated that light might follow the shortest possible path in curved space. He postulated that the presence of matter and energy curved the fabric of space-time itself, akin to how a heavy mass placed on a trampoline deforms its surface. This curvature created an illusion of the light beam bending, analogous to a marble orbiting around the heavy mass on the trampoline without any applied force. Extending this concept, Einstein proposed that the Sun, acting as a massive gravitational body, curved space around it. Consequently, objects, including planets like Earth, followed curved paths in this distorted space-time, giving rise to the phenomenon of gravitational attraction. This revolutionary idea described how matter and energy dictate the curvature of space-time, causing nearby objects to move along curved trajectories, essentially falling towards regions of warped space created by massive bodies like stars or planets. This pivotal revelation laid the groundwork for Einstein's theory of general relativity, offering a comprehensive framework to understand the gravitational interactions shaping the dynamics of the universe. Albert Einstein's theory of general relativity introduced a groundbreaking concept by integrating time into the fabric of the universe alongside space. This integration created the unified concept known as space-time, where time is inseparable from the three dimensions of space. Einstein's earlier theory, special relativity, postulated that the speed of light remains constant for all observers, regardless of their motion or state of rest. When considering light traveling from one point to another, from point A to point B, in the presence of a massive object like the Sun, general relativity predicted that the path of light would curve due to the Sun's gravitational field. This curvature would effectively lengthen the distance the light beam travels, suggesting that it would take more time for light to move from point A to point B in the Sun's gravitational influence. However, this idea conflicted with the theory of special relativity, which dictates that the speed of light is constant and independent of the observer's frame of reference. To reconcile this conflict, Einstein proposed that time itself must adjust or dilate in the presence of gravitational fields. According to gravitational time dilation, time moves at a slower pace near massive objects in space and speeds up farther away from them. For instance, time for individuals on Earth would pass more slowly compared to astronauts aboard the International Space Station, ISS, a phenomenon that has been experimentally confirmed through various observations and experiments. One profound confirmation of Einstein's theory was the phenomenon known as gravitational lensing. Arthur Eddington, an astronomer, conducted an experiment during a solar eclipse in 1919, observing the position of stars behind the Sun. According to general relativity, the Sun's gravity would bend the light from these stars, causing their apparent positions to shift. Eddington's observations confirmed this prediction, providing early empirical support for Einstein's theory and solidifying its credibility. Over the years, numerous experiments and observations have validated Einstein's theory of general relativity. The predictions made a century ago continue to be confirmed by modern scientific observations, allowing us to peer into the universe through a new lens provided by Einstein's groundbreaking insights. Thank you for joining us on this enlightening exploration into Einstein's journey to conceive the theory of relativity. If you found the revelations about Einstein's thought process as intriguing as we did, don't forget to hit the like button and share your thoughts in the comments below. For more compelling insights into scientific discoveries and the wonders of the universe, subscribe to our channel and stay tuned for our upcoming explorations. Remember, the pursuit of knowledge and imagination knows no bounds. Until next time, keep questioning and seeking understanding. Thank you for watching.